Calculating the pH in solutions of weak acids is not as straightforward as it was for strong acids. For strong acids, the pH could be figured out by knowing the initial concentration of the strong acid, which we'll call HX. Often the hydrogen ion concentration was the same as the concentration of the acid if it was a strong monoprotic acid, meaning it had one ionizable proton. We looked at the reaction stoichiometry to figure out the hydrogen ion concentration, which for a lot of strong acids, it was 1:1. And so we could calculate the pH directly. But for a weak acid, they are not fully ionized, and we don't know how much they're going to ionize just by looking at the weak acid. So there's an equilibrium situation set up. For the weak acid, the initial concentration of the acid, HA, will not be equal to the hydrogen ion concentration. So we're going to have to do a little bit more work in order to figure out what our hydrogen ion concentration is at equilibrium. Once we find that hydrogen ion concentration, we can then use it in our pH calculation. So for any generic weak acid, which we'll call HA, if it reacts with water, it'll form a little bit of hydronium ion and a little bit of A-, the conjugate base. Because there is an equilibrium set up between all the species, we can write our equilibrium expression. We would have our products hydrogen ion concentration times that conjugate base A- concentration on the top, divided by the concentration of our weak acid itself. We don't include the water in our expression because it's a pure liquid. So we would have our K equal to H plus times A- over HA. And now we call the K, K sub A. The A stands for acid. Ka is referred to as the acid ionization constant. The stronger the acid, the larger the value of the Ka will be. If you look at the top of your acid-base ionization chart, you'll notice all the strong acids are in the top left corner, and they have a Ka that just says large. That's because for a strong acid, we'll never actually write an equilibrium expression because the strong acid ionizes 100%. We only use Ka values for weak acids. So as you're looking at your chart, you'll see that going from top to bottom on the acid side, the Ka values are getting smaller and smaller and smaller as you go down, and that means the acids are getting weaker and weaker and weaker. So weak acids have a Ka that is smaller than 1, and it can vary a lot depending upon how strong or how weak that weak acid is. Another term that's used to discuss acid strength is the pKa of an acid. The pKa is calculated much like how the pH or the pOH would be calculated, by taking the negative log, this time of the acid ionization constant, which is the Ka of the acid. As the pKa gets lower, the Ka would get bigger. So there's an inverse relationship between the two. A lower pKa equals a higher Ka. And we said that a higher Ka was a stronger acid. So a lower pKa refers to a stronger acid. You could see even negative pKa values for some of the very, very strong acids. So there's an inverse relationship between those two, just like there is for pH and hydrogen ion concentration. So a lower pH meant a higher hydrogen ion concentration, which meant a stronger acid. If we were to take a weak acid and dissolve it in water and calculate the pH of the solution, we could use that pH to work backwards and figure out an unknown Ka or pKa for an acid. Usually all the values are tabulated on the chart for us and we'll use them later, but if we needed to figure out a Ka, we could do that from our pH information. So we have a 0.25 molar solution of hydrofluoric acid. Hydrofluoric acid is a weak acid, and it has a pH of 2.04. What are the values of Ka and pKa for HF? So starting out, we're going to want to write our dissociation for our weak acid. So hydrofluoric acid will break up in solution into hydrogen ion and fluoride anion. And anytime we're dealing with an equilibrium situation, we would want to write an ice table. Our initial concentration of the hydrofluoric acid would be the concentration we were given, which is 0.250 molar. And initially we would assume that we have 0 hydrogen ion formed and 0 fluoride anion formed. Hydrofluoric acid will dissociate or ionize to some extent, and we call that change minus X. Everything in this reaction has a 1-to-1-to-1 stoichiometric relationship. So when hydrogen ion forms, it'll form in the ratio of plus X, and fluoride will be the same, plus X. So our equilibrium line would be 0.250 minus X, hydrogen would be X, and fluoride would be X. We can now write our equilibrium expression. Ka would be equal to the hydrogen ion concentration times the fluoride ion concentration divided by the concentration of hydrofluoric acid. Now remember, what you plug into your equilibrium expression has to be equilibrium concentrations. So everything we plug in over here has to correspond to something from our E line, which represents equilibrium. In this example, we're trying to calculate the Ka. So we're going to have to be able to know everything on the right-hand side of our equilibrium expression. And from our pH, we can actually figure out what our X value is, or our hydrogen ion concentration at equilibrium. The hydrogen ion concentration will be equal to 10 raised to the negative pH power. So that'll be 10 raised to the negative 2.04. That gives us a hydrogen ion concentration of 9.12 times 10 to the negative third molar. That is essentially our X value. That concentration is hydrogen ion at equilibrium. And that concentration is also equal to the fluoride ion concentration. It's the same. So 9.12 times 10 to the minus third equals hydrogen ion and fluoride ion concentration. We could solve for our hydrofluoric acid concentration, HF, by taking, according to the equilibrium line, 2.50 minus X. So that'll be 0.250 minus 9.12 times 10 to the negative third. So our HF concentration comes out to being 0.241 molar. So now we know everything on that equilibrium line, and we have all the concentrations that we can substitute in to the right-hand side of our equilibrium expression to actually solve for the unknown acid ionization constant. So Ka was equal to the hydrogen ion concentration at equilibrium times fluoride ion concentration over our weak acid concentration. We figured out that our hydrogen ion and our fluoride ion concentration were the same. Those were both going to be 9.12 times 10 to the minus third divided by our equilibrium concentration of hydrofluoric acid, which was 0.241 molar. So our Ka comes out to being 3.45 times 10 to the negative fourth. And to calculate our pKa, we'll take the negative log of our Ka, which is negative log of 3.45 times 10 to the negative fourth power. And our pKa is about 3.46. So in order to calculate our Ka, we had to be able to figure out all those equilibrium concentrations on the right-hand side. And then once we knew our Ka, we could use that relationship between pKa and Ka. We can also calculate equilibrium concentrations of species or the pH of the solution by using a known Ka value for a weak acid. Determine the equilibrium concentration of all species and the pH of a 0.10 molar HC2H3O2 solution, and that is acetic acid. So we have a weak solution of acetic acid, and we want to figure out the concentrations of all species and the pH. So first we're going to start by writing the dissociation of our weak acid equation. So acetic acid will break up into hydrogen ion and its conjugate base, which is acetate anion, and we'll make our ice table. Our initial concentration we were given of our acetic acid was 0.1 molar, and initially we have 0 of our products, so 0 hydrogen ion and 0 acetate before any ionization occurs. And when acetic acid breaks up, we don't know how much it's going to break up into, so we call that minus X. And our products are going to form by plus X. Once again, make sure you look at the stoichiometry to determine the ratio. So we have 1 to 1 to 1 here, so we only have minus X and plus X. Our equilibrium line then will be 0.10 minus X for our acetic acid, and it'll just be X for our hydrogen ion and X for our acetate anion. From that line, we can then use that in our equilibrium expression. So our equilibrium expression will be Ka equal to concentration of hydrogen ion times concentration of acetate anion over the concentration of our weak acid. If we're going to figure out what the concentrations of those 3 species are at equilibrium, we're going to need to know the left-hand side of the equation, or the Ka. You can look this up on your acid ionization chart. So you're going to want to find acetic acid on there and look up what the Ka value is for acetic acid. Once you find it, you should see that the Ka for acetic acid is 1.8 times 10 to the negative 5th. So we can plug that in for our Ka and then substitute everything from our equilibrium line into our equilibrium expression now. So hydrogen ion at equilibrium was X, acetate at equilibrium was X, and our weak acid, acetic acid concentration at equilibrium was 0.10 minus X. Now notice for our weak acid, our Ka value is very small. Typically we're looking for it to be smaller than 10 to the minus 4th. So in this case we have a value of 10 to the minus 5th. That means that we can simplify our equilibrium expression even more because we can ignore this minus X term. And that's kind of the nice thing about doing weak acid calculations. Since we know they're weak acids, on your chart you'll see that most of them have a Ka value that is 10 to the minus 4th or smaller, allowing you to make this simplifying assumption. So we can rewrite our simplified equilibrium expression as 1.8 times 10 to the negative 5th equals X times X is X squared over just 0.1 molar for that equilibrium concentration of our weak acid. When we multiply 0.1 by 1.8 times 10 to the minus 5th, that gives us 1.8 times 10 to the negative 6th, and that's equal to X squared. So next we have to take the square root of both sides to figure out what X is. So we should get X is equal to about 1.3 times 10 to the negative 3rd. And that concentration is molarity, and that's equal to our hydrogen ion concentration, and X was also equal to our acetate anion concentration. So those 2 species we have the equilibrium concentrations for now. The last species we had to calculate the concentration of was the acetic acid itself. And so that was going to be 0.1 minus X. So that'll be 0.1 minus 1.3 times 10 to the negative 3rd. And that gives us a concentration of our acid of 9.87 times 10 to the negative 2. So that's really close to being about 0.1 molar still. So our equilibrium concentration of acetic acid is about the same as it was initially because of the fact that it didn't ionize very much. It only ionized a small amount. Lastly, we're supposed to calculate the pH of the solution. The pH will be equal to the negative log of the hydrogen ion concentration. So we'll take negative log of our X value, which was 1.3 times 10 to the negative 3rd, and that gives us a pH of 2.88 for a 0.1 molar acetic acid solution. Let's try another example with a weak acid. A vitamin C tablet containing 250 milligrams of ascorbic acid, which is HC6H7O6, Ka for that acid is 8.0 times 10 to the negative fifth, is dissolved in 250 milliliters of water. What is the pH of the solution? The molar mass of ascorbic acid is 176 grams per mole. So you always want to start with writing your dissociation of your weak acid. So we have HC6H7O6, and when that weak acid dissociates, it'll lose a proton and we'll be left with its conjugate base, which will be C6H7O6 minus. We're going to want to construct our ice table. And we were not given an initial concentration for our weak acid, so we're going to have to calculate that. We know we have 250 milligrams of it, and it's dissolved in 250 milliliters of water. We need to figure out the molarity of our weak acid in order to use it in our ice table. So starting with 250 milligrams of ascorbic acid, we'll just call it AA for short, we can convert that to grams. There's 1,000 milligrams in every gram. And then we can use the given molar mass to convert to moles. So 176 grams for every 1 mole of ascorbic acid. And since we need concentration, we need moles per liter, we can divide by the volume in liters. It was dissolved in 250 milliliters, which corresponds to 0.250 liters. So then notice your units, your milligrams cancel, your grams cancel. You're left with moles of ascorbic acid per liter. So this will give us our molarity that we can use in that ice table. It comes out to being 0.00568 molar. So that's our initial concentration of the ascorbic acid. So let's plug that in for our I line. We're going to have 0.00568, and initially we have 0 hydrogen ion and 0 of our conjugate base because it hasn't broken up yet, hasn't ionized yet. The change, we have a 1 to 1 to 1 ratio. So our change, it's going to go down by minus x. Hydrogen ion will form by plus x. The conjugate base will form by plus x. And our equilibrium line then is going to be 0.00568 minus x, and then x and x. We also want to write our equilibrium expression each time we're dealing with a weak acid. So Ka will be equal to hydrogen ion concentration times C6H7O6 minus concentration all over our weak acid concentration, HC6H7O6 for the ascorbic acid. And we're going to take our equilibrium line concentrations and we're going to substitute them in to our equilibrium expression. We were given the Ka for this acid. If we weren't, we could have looked it up, but 8.0 times 10 to the negative fifth is our Ka. And once again, it's small. So we have a weak acid. We're going to have a small Ka most of the time, but you should make sure that you get in the habit of double checking that it's at least 10 to the minus fourth or smaller. So we can make that simplifying assumption because 10 to the minus fifth is less than that. So we're going to get to ignore that minus x. That's the amount that our weak acid actually dissociates. So it's going to be such a small amount that we wouldn't really be able to subtract it anyways from our initial concentration according to significant bigger rules. So substituting everything into our equilibrium expression, we got 8.0 times 10 to the minus fifth, that's our Ka. That's going to be equal to x times x on the top over 0.00568 on the bottom, and we're ignoring that minus x. So we're going to have essentially x squared over 0.00568 for our initial concentration. For x squared, we're going to get that equal to 4.54 times 10 to the negative 7th when we multiply the Ka by the initial concentration. And then to get x, we'll take the square root of both sides. And so x is equal to 6.74 times 10 to the negative 4th. And x was equal to our hydrogen ion concentration, and it was also equal to our conjugate base. Now, in this question, we were just asked for the pH of the solution. So really what we care about is that our x was our hydrogen ion concentration. So now we can use that in our pH formula. pH is the negative log of the hydrogen ion concentration. So we'll take the negative log of 6.74 times 10 to the negative 4th, which gives us a pH of 3.17. And you should expect a low pH. pH less than 7, the solution is acidic. If you had gotten a pH that was 7 or higher, you would have known that you made a mistake somewhere along the way, because we should have expected it to be relatively low. Strong acids have a pH of 2 or less usually, whereas weak acids will have a pH of 2-ish up to high 6s before it hits that neutral point. So that's just kind of a double check you can do at the end to make sure your answer actually makes sense. The percent dissociation or percent ionization of a weak acid is another way to talk about the acid's strength. The percent dissociation describes how much the weak acid actually breaks up into its ions. Percent dissociation can be calculated by taking the amount of the weak acid that dissociates divided by the initial concentration of the weak acid times 100%. The amount of the weak acid that actually dissociates or ionizes is the exact same as the H+ concentration at equilibrium, which is often our X value. When we compare different acids with different Ka values, the larger the value of Ka, the stronger the acid we said, and that means it'll have a greater extent of dissociation. So as Ka goes up, percent dissociation goes up, the amount of hydrogen ion at equilibrium goes up, and we have a stronger acid. Remember that strong acids are 100% dissociated. And so we don't usually talk about a percent dissociation for strong acids because we know that they're broken up 100%. Usually, most weak acids will have a percent dissociation of maybe 5 to 6% or less. So of all the weak acids that are actually present, they're only ionized or dissociated a very, very small amount. Most of the weak acid stays together in its combined molecular form. A 0.1 molar solution of butanoic acid has a percent deprotonation of 1.23%. Determine the pH of the butanoic acid solution. So our formula for percent dissociation or percent deprotonation is equal to the amount of the weak acid that dissociates divided by the initial concentration of the weak acid. And it's listed as a percent, so we multiply by 100. That amount of weak acid that dissociates, which is our numerator, that's going to be the exact same as the hydrogen ion concentration, because however much of the weak acid actually breaks up is how much hydrogen ions formed and how much conjugate base is formed. So those two will be one and the same. So that's what we're actually going to want to figure out if we're going to determine the pH of the solution. So our percent dissociation is 1.23%, and that's going to be equal to our hydrogen ion concentration over our initial concentration, which we were told that was 0.1 molar, times 100. So if we divide both sides by 100, we're going to get 0.0123 is equal to our hydrogen ion concentration over our initial concentration, 0.1. So we'll multiply by 0.1 to get that out of the denominator, And that'll give us our hydrogen ion concentration of 0.00123. Next, to calculate the pH, we're going to take the negative log of that hydrogen ion concentration. And so that'll be the negative log of 0.00123. And that gives us a pH for our butanoic acid solution of 2.91. Once again, make sure that you're getting a pH that is less than 7 because you have an acidic solution. Let's try another example with percent dissociation. Calculate the percent ionization of a 0.125 molar solution of nitrous acid, HNO2, with a pH of 2.09. So nitrous acid is a weak acid, and when it ionizes, it's going to break up into H+ and NO2-, which is the nitrite ion. And we can figure out from our given pH what the hydrogen ion concentration is and use that in our percent dissociation formula. So the hydrogen ion concentration will be equal to 10 to the negative pH, which is 10 raised to the negative 2.09 power. And our hydrogen ion concentration comes out to being about 8.13 times 10 to the negative third molar. That hydrogen ion concentration is how much our weak acid actually dissociated. So in our formula, that's equal to HA dissociated. So our percent dissociation is equal to the amount of our weak acid that dissociated, which is the same as the hydrogen ion concentration at equilibrium, divided by our initial concentration of our weak acid, and then times 100. So our dissociated amount we calculated to be 8.13 times 10 to the negative third molar. The initial concentration of the weak acid, we are told, is 0.125 molar. And then that fraction times 100% gives us a percent dissociation for nitrous acid of 6.5%. There are many acids that contain more than one ionizable proton. These are called polyprotic acids, and they don't lose all of their protons in one step. The protons dissociate in a stepwise process one at a time. So some examples of polyprotic acids are H2CO3, carbonic acid, H2SO3, sulfurous acid. Both of these have two ionizable protons, so they're referred to as diprotic acids. H3PO4, phosphoric acid. 3 ionizable protons for phosphoric acid. This is called a triprotic acid. And the only strong acid that is a diprotic acid is sulfuric acid, H2SO4. Sulfuric acid has 2 protons that it could give off. When a polyprotic acid loses its protons, it's going to lose them in a stepwise manner. So we can write the stepwise dissociation for carbonic acid, which is going to have 2 steps to lose both of its hydrogen ions. First, we would start with H2CO3, and initially it's going to lose 1 of its hydrogen ions, and the conjugate base of carbonic acid will be the hydrogen carbonate ion. HCO3- will be left over when 1 proton is lost. And notice the conjugate base of our acid can be an acid itself. So the hydrogen carbonate ion has another proton that it could lose. So starting now with hydrogen carbonate, HCO3-, we can write the dissociation for that species as an acid. It can lose that 1 proton out front now, and that's the last one. It'll dissociate into hydrogen ion, and we'll be left with CO3-2-, which is just the carbonate anion. So hydrogen carbonate can be an acid, and its conjugate base would be carbonate. HCO3-, the hydrogen carbonate ion, is said to be amphoteric. It's a species that could function as a base or as an acid, depending upon who it's reacting with. But this represents the two-step dissociation of carbonic acid. So at equilibrium, the species that would be present in your flask, so if this is our flask, both of those reactions are going to occur, and we would have some molecular carbonic acid, we would have protons present, we would have hydrogen carbonate present, and we would have the carbonate ion present at equilibrium, because we're going to have both of those dissociations occurring. Each one of our acid dissociations would correspond to its own acid ionization constant. So for our first step, we could look up a Ka1, and for our second step, we could look up Ka2. Ka1 would correspond to the Ka for carbonic acid, whereas Ka2 would correspond to the Ka for hydrogen carbonate ion. Write the stepwise dissociation for phosphoric acid, H3PO4. So phosphoric acid is a triprotic acid. We're going to have 3 steps for the ionization. So H3PO4 will first dissociate into H plus and H2PO4 minus when it loses 1 proton. Phosphoric acid's conjugate base is the dihydrogen phosphate ion. Dihydrogen phosphate can also be an acid though, because it has 2 protons that it could lose. So now this next step will be starting with H2PO4 minus dihydrogen phosphate dissociating into hydrogen ion, and HPO4 minus, which is the hydrogen phosphate ion. So dihydrogen phosphate could be an acid, and then hydrogen phosphate would be its conjugate base. That hydrogen phosphate ion can also be an acid though. So it could lose its proton in a third step. HPO4 minus can ionize and break up into hydrogen ion. And what would be left with would be PO4 minus, the phosphate ion. So hydrogen phosphate as an acid, and then its conjugate base, which is phosphate ion. So for this dissociation, there would be 3 individual steps and 3 individual acid ionization constants. So we could look up Ka1. Ka1 would correspond to the Ka for phosphoric acid. We could look up Ka2. Ka2 would correspond to dihydrogen phosphate as an acid. And Ka3 would correspond to the hydrogen phosphate ion as an acid. So at equilibrium, for this weak acid dissociation in your flask, you have a lot of species present now. You've got phosphoric acid present. You've got hydrogen ion from 3 separate steps that was created. You've got dihydrogen phosphate ion. You've got hydrogen phosphate ion present, and lastly you have phosphate ion. So we would need to figure out the concentration of all of those species at equilibrium if we were going to talk about everything in our flask. Calculate the pH and the concentration of all species present in a 0.2 molar carbonic acid solution, H2CO3. So here we have a polyprotic acid. Carbonic acid is going to be diprotic, so if we write our 2 dissociations, we're going to have H2CO3 breaking up into H plus HCO3 minus hydrogen carbonate. We'll look up what Ka1 is for the first step. The second step is going to be the hydrogen carbonate ion dissociating into H plus the carbonate anion CO3 minus. And we'll look up Ka2 for our second acid losing a proton. Ka1 off of our acid ionization chart for H2CO3 is equal to 4.3 times 10 to the negative 7th power. And Ka2 off of our acid ionization chart for HCO3 minus is equal to 4.8 times 10 to the negative 11th power. So it's quite a bit smaller than Ka1 because the hydrogen carbonate ion is a weaker acid than even carbonic acid. So HCO3 minus is a weaker acid than H2CO3 is, because H2CO3 has a larger Ka value. Now, something that will help us with our calculations to make this a little bit easier is to know that since H2CO3 is stronger than hydrogen carbonate, when carbonic acid dissociates, the amount of hydrogen ion that's formed, the majority of it comes from the first step. So the majority of the hydrogen ion is produced in the step 1. The amount of hydrogen ion that's produced in step 2 is very small compared to the first amount. So we'll be able to use this fact when doing our calculations to simplify them a little bit. So let's look at each of these two equilibria separately. So if we break this up, now I'm just looking at the first dissociation, H2CO3 dissociating into H plus hydrogen carbonate, HCO3 minus. We can write our ICE table for the dissociation of our weak acid. Our initial concentration of carbonic acid, we were told, is 0.2 molar. Initially, we have 0 hydrogen ion and 0 hydrogen carbonate ion. The amount that the carbonic acid dissociates is going to go down by X. The amount that the hydrogen ion forms is plus X, and the hydrogen carbonate ion is plus X. At equilibrium, we're going to have 0.20 minus X, X for the hydrogen ion, and X for the hydrogen carbonate ion. When we write our equilibrium expression, we're going to have Ka1 is equal to the hydrogen ion concentration times the hydrogen carbonate ion concentration divided by the concentration of carbonic acid at equilibrium. And our Ka1 value is going to be 4.3 times 10 to the negative 7th, and this is a very small value for Ka. So since it's small, again, we get to make that simplifying assumption where we ignore any x's that are added or subtracted, never multiplied or divided. So the only x that we have that's subtracted is 0.20 minus x. So we're going to ignore that minus x there to simplify our math. Substituting everything into our equilibrium expression, we have 4.3 times 10 to the negative 7th as our Ka equals x times x, so that'll be x squared, all over our initial concentration of carbonic acid, which was 0.20. X squared is equal to 8.6 times 10 to the negative 8th, and taking the square root of both sides, we get x is equal to 2.93 times 10 to the negative 4th power. And that value was equal to 2 of our species concentration. That was equal to the hydrogen ion from the first step, which was equal to the hydrogen carbonate ion concentration. So both of those are 2.93 times 10 to the negative 4th molar. And our initial concentration of our H2CO3 is going to be equal to 0.20 minus x, which will be 0.20 minus 2.93 times 10 to the minus 4th, which comes out to being approximately 0.20, very close to that, 0.199 molar. So we have a few of our species concentrations at equilibrium so far. We've got our hydrogen ion and our hydrogen carbonate ion. And we've also got our concentration of carbonic acid, H2CO3. Now, since most of the hydrogen ion comes from the first step, we can assume that this is essentially all of our hydrogen ion concentration. The second step was the hydrogen carbonate ion acting as an acid, dissociating into hydrogen ion plus carbonate, which is CO3 2-. So now if we set up an ICE table for our second step, our initial concentration of hydrogen carbonate, we just calculated. That was equal to our X value. So we have 2.93 times 10 to the minus fourth as our initial concentration of hydrogen carbonate, but we also initially have in our flask some hydrogen ion. That was the same amount as the hydrogen carbonate from that first dissociation. So hydrogen ion initially is also 2.93 times 10 to the minus fourth. Initially, we have no carbonate ion though. That hasn't formed yet. When hydrogen carbonate ionizes and loses its proton, it's going to go down by X. So the change will be minus X. When hydrogen ion forms, it's going to form by plus X. And when carbonate forms, it will form by plus X. So at equilibrium, we're going to have 2.93 times 10 to the minus fourth minus X for hydrogen carbonate. The same for the hydrogen ion, 2.93 times 10 to the minus fourth plus X. And then carbonate will just be plus X. So in this case, technically we're supposed to form a little bit more hydrogen ion from this second dissociation step. It'll be what we had initially plus X, however much the hydrogen carbonate ion dissociates. Our equilibrium expression here is going to be Ka2 is equal to hydrogen ion concentration times carbonate ion concentration divided by our initial concentration of our weak acid, which is HCO3 minus. And if we look at what our Ka2 is, it's very, very small, 4.8 times 10 to the minus 11th off of our acid ionization chart. This is significantly smaller than even our first Ka1 was. So whatever our value for minus X is and for plus X here, it's going to be such a small amount that we're going to ignore both of those. So we're really not going to even assume that any substantial amount of hydrogen ion is formed from that second step. So really what we're going to have to figure out then is just what our amount of carbonate ion is at concentration at equilibrium, and that's just going to be our X value. So now using our Ka2, we're going to have 4.8 times 10 to the negative 11th is equal to our concentration of hydrogen ion, which that came from the first step, 2.93 times 10 to the minus fourth, times the concentration of our carbonate ion, which we'll just call that X at equilibrium, divided by our concentration of our hydrogen carbonate ion, which that was the same as the hydrogen ion because they were 1-to-1 in the first dissociation. So that'll just be 2.93 times 10 to the negative fourth as well. So notice that since our hydrogen ion concentration and our hydrogen carbonate ion concentration are the same, those two terms essentially cancel, and our X ends up being equal to our Ka2. So X is equal to 4.8 times 10 to the minus 11th. And what that was, X was equal to our carbonate ion concentration, CO3 minus. So now we have the concentrations of all species present at equilibrium. We were also asked for the pH of the solution. So the pH will be equal to the negative log of the hydrogen ion concentration. So we'll take the negative log of 2.93 times 10 to the negative fourth power, which gives us a pH of 3.53.